All right, I think we are live. Awesome. Hey everyone, my name is Niels Bantilan. I'm at the ML/AI team at Union.ai, and I'm going to do a quick workshop on how to build self-healing agents. Agents are all the rage this year. I have myself been using them a lot and building my own for various use cases at the company. And yeah, I wanted to run through a quick example of what that might look like building one from scratch on Flyte. Flyte is a machine learning and AI orchestrator, and helps you build everything from data to ML pipelines, as well as agents, as you'll see. And self-healing is kind of a buzzword right now, and I think a useful thing I like to do when I encounter these kinds of buzzwords is try to figure out what it actually means to implement the thing that the buzzword is referring to. So without further ado, let me share my screen. And just as a preamble, there's basically two ways of engaging with this right now. You can either just watch me run stuff and see things happen, or you can actually code along yourself. If you signed up for the event, you should have actually access to a Tri-V2 cluster. Let me just head over to this project right here. 1 second. Yeah, so if you signed up, you should be able to go to tryv2.hosted.unionai.cloud, sign in through the email that you signed up for the event on. So it should look something like this when you sign in. You can sign in via Google typically. And yeah, if you want to code along and run things, you can do so here. Just a quick caveat, this Tri-V2 cluster is basically a little demo environment for folks to try Flyte 2 on. It literally has 5 T4 GPUs, and so we'll be using those today, and some limited number of CPUs. So hopefully, we haven't had this problem in the past of a lot of people running stuff. But as you can see, I have something running right now. And yeah, without further ado, can head over to Union.ai workshops if you want to follow along with the code at least. It's under tutorials/auto research. So as you can already tell, this workshop will go through kind of adaptation of Andrej Karpathy's auto research repo, which is, wow, 55,000 stars. Yeah, it's very popular right now. Just to give a bit of background before jumping into the repo, basically what this is, it's a fairly straightforward agent harness that I believe uses Anthropic. Not sure exactly the details here. It might actually use like a local model. Let's see. Yeah. Anyway, it uses some kind of LLM to write training code. And so what it's doing is it's taking a data set, that's fixed. The data set is, this repo is kind of changing a lot, but now it's Tiny Stories GPT-4 Clean. The data set we'll be working with in our repo is the climb mix 400B shuffle. I think that's what the data set was at the time of me working out this workshop. And so it's a static data set, basically a bag of tokens. And we're going to take a baseline LLM architecture and have the LLM agent edit a train.py file. So it has a dataset preparation file that it can't change. It's not allowed to change. And a train.py file that it is allowed to change. And in this file, as we'll see later, there's a eval metric that we're using to assess whether or not any code change to this file is good. We're measuring it by bits per byte. You can think of that as a measure of surprise or how well the LLM is predicting the next token. So lower here is better. We're not going to run enough experiments to see this type of plot, but we are kind of going to go through the mechanics of how to build something like this with Flyte and see how some of Flyte's properties give it a little bit more of a reliability story around catching errors, making sure that you can provision the right resources based on the training script, and things like this. Okay. So hopping over to the repo, if you want to run things, you can actually go to the repo and start a code space. I would actually, recommend, didn't mean to do that. Let's delete this one. Okay. I would actually recommend creating a code space that has 4 cores, just because we're installing PyTorch and a bunch of other stuff. So pick this option when you're creating your code space. I have one running already, which is over here. So when you get here, I'm just going to walk through all the setup steps, just in case someone right now or in the future watching this recording wants to run this. So you'll start out in the root of the repo. And first you want to cd into the auto research directory, and then install UV, run UV sync to install all the dependencies, and activate the virtual environment. Next, you'll want to export the Flyte project we'll be working in. I already showed you the UI here a little bit, but the project we're going to be in is Agents March, because it is March, and we're doing an agent workshop. And then we're going to create a Flyte config file. In the virtual environment, you should have the Flyte CLI ready to go. So you can go ahead and create a config file. I'm going to overwrite the one that I have currently. And all that's going to do is create a config.yaml over here. And that just points to the try-v2 cluster with some configuration here for the CLI to know where and how to run stuff. An optional step here is to add your own Anthropic API key secret. I already have one set up for this workshop, but for future reference, basically if you run this command to create a secret in your project, you would then have to go into the auto research agent.py file and edit the code snippet here that requests for a specific secret key. So that is optional. I have one loaded already into the project. Yeah, we just go into some of the details here for those of you who are curious. So we're just going to download a subset of the full data set while also downloading the validation shard. So the data sets are sharded up, I think, as Parquet files. And this shard happens to be the validation set. Going to use some byte pair encoding tokenizers, tokenizer, using these dependencies. And yeah, we'll take a look into the guts of the agent. But basically, we're gonna have the agent, which lives here in auto research agent, go through a loop that we configure, loop n number of times through attempts at increasing the performance of the model by decreasing bits per byte on the validation set. And you can think of this as really like fancy hyperparameter optimization. So yeah, instead of having a fixed architecture and changing the hyperparameters in that architecture, you actually have a baseline training script, and the hyperparameters, so to speak, are the symbols and tokens in that script that the model can edit. As I said earlier, the agent is going to modify this train.py file, so a pure Python file, and it'll use this prepare.py file as unchangeable static data prep and data loading prep, and I think eval logic. We have some other files in here that's more Flyte specific, so types just defined with some data classes to help us reason about our agent. And report, as the name suggests, will help us build visualizations and reports for what's going on as the agent is running. Okay, so I'm going to go ahead and run the agent. And as it's running, because we're doing a lot in here, I actually, before running this, I'm just going to take a peek into my research agent and see. Okay, so I'm going to have it do 10 rounds of weird. 1 second. Okay, great. I'm going to have it do 10 rounds of edits on the training script. You feed it, some user intent, basically a user prompt. I have an optional argument here to research a topic to find relevant papers on arXiv, which we're going to disable for now. So let's go ahead and run this. Let the workshop gods be kind today. Okay. So when you first run this, you're going to get a login URL. So that's just going to get our GitHub code session running. And yeah, I think it's going to ask multiple times. I forgot to install keyrings alt, which actually will prevent this. Actually, let me go ahead and do that. If you haven't already, okay, let's see if that works better. Okay, I'm going to try signing in again. Okay, great. So what's happening now is we're building an image that we're going to run this agent on. This is something that Flyte does on the remote builder. So this is the Union hosted remote builder. And just to clarify, Union is the commercial company that is supporting Flyte, which is an open source product. So that while that builds, I think we can start dissecting what exactly is going on in this agent file. So let me just move this down a little bit. So the entry point is pretty simple, right? The interface is this auto research agent. You give it a research topic that's optional, user intent, what you want the agent to do. We're prompting it to start with a small but reasonable GPT baseline, tuning depth and width, minimize validation bits per byte. We're also just going to download 4 shards for the training set, 4 shards of the data. I haven't quite counted how many data points that is exactly, but we can say like a couple hundred or 1,000. And then we say how many experiment rounds to give it. So you could set this to, 100 or 1,000. So the guts of this agent goes as follows. We first do there's a bunch of preamble we need to do, right? So the first thing we're going to do is we're going to build the data set. We're going to download it, and we're actually going to profile that data set. So we'll see what that looks like in a second. Once it's started running, I can point you to, I guess, this one that's completed. So this only ran 3. We see that there were bugs in the first 2 experiments, and then it kind of fixed it up the third one. So let's look at the research bundle here. So here we downloaded 4 shards. When we profiled it, you can see that it's about 128,000 bytes in this data set, 5 4K files. These are the shards, and this is the validation shard. So these are tokenizer bytes. The number of data bytes are roughly, 500, close to 500 million. So hop back onto the script. So that's kind of the preamble. Here's the optional research topic archive paper retrieval step. So we skip that. And then the first thing we do is take a first pass at writing the training code, right? So here we're going to read in our baseline training script, which is literally this file right here, right? So this is kind of an adapted version of an earlier version of the original forked auto research repo. So as you can see, uses PyTorch, implements causal self-attention, all the different components, defines a top-level tiny GPT module, uses Atom for its optimizers. It goes through a training loop within some time budget, which we set in this case to 60 seconds. And takes in the literature, which is optional, takes in the dataset profile and user intent, and then you can find the training up here. All this is doing is it's calling an LLM based on, so this is not, ideally you'd want some kind of agent harness like Claude Code to do this. So in this simpler example, we just do a single shot LLM call to generate the training code. So this you can see is a Flyte trace. A Flyte trace is a helper function that effectively gets visualized in the UI. So this little smaller circle is a Flyte trace, in contrast to a Flyte task, which actually is a containerized function. So this runs in its own container. And that's nice because you can get container isolation across all your tasks and then call Flyte traces to get extra observability without having to spin up a new container. So this creates a title for the experiment and code, Python code to run. And then based on this code, we do another LLM call that provisions resources. And so if you look up at the Flyte trace function that implements this, here's a system prompt. You can go read it more in detail, but basically it stringifies all of the data here, and then creates a JSON, basically a dictionary of arguments that will feed into Flyte.resources. So Flyte.resources is a way to access, I guess there's no code complete here, but it gives you a way to declaratively request what resources you want out of your container, right? So you can see where I'm going here. We're giving the agent actually the ability to define its own resources. So here's the instruction for that. Basically, in the end, it outputs a JSON, a dictionary JSON-like object with CPU, memory, and GPU requests. And right here, I only give it one type of GPU, which is a single T4. On a more powerful cluster, you could request, A100s, H100s, and let's say 2 of them or 8 of them, if you are so lucky to have access to those things. Okay, so hopping back down to the agent body. So what have we done so far? We've created our data set and profile. We've created our first pass at the, hopefully improvement in our training code. We've provisioned resources for it, or we've defined resources for it. And now here's the for loop. And just to point out that in Flyte 2, it's basically just Python. And so you can do for loops, while loops, try except, if else statements, conditionals, and basically you can structure your workflow as a execution graph, no longer a DAG, right? Directed acyclic graph. So it's an execution graph, a tree basically that looks kind of like this. And inside of here, we're doing a couple of things, and this is where I'm starting to. I'll mention the word self-healing, and I'll say how this is actually an implementation of that idea, both at the logical level and at the infrastructure level. So what we're going to do is we're going to run our code in a training subjob. And what this training subjob is just kind of a wrapper task that then downstream kicks off a sandbox container. So this Flyte sandbox is Flyte's own native sandbox support. This has limited I/O inside the container, so it can only read from a specific inputs directory and write to a specific outputs directory. And also it's configurable so that it has limited network access. And even then, the worst case scenario is Flyte has network policies that by default restrict any potential catastrophic hack that happens in any given container. So even if your agent is compromised and starts reading and executing a lot of insecure code, as we saw with the Light LLM supply chain attack recently, the blast radius of any such attack will be limited based purely on the architecture of how Flyte works. Okay. So we're going to, into the sandbox, we're going to pass in the code, give it some inputs. We're going to give it the data, the tokenizer that we pre-trained, the prepare.py file that is basically like the static constant data prep in eval logic. You're going to say you're going to output a JSON string of metrics. We're going to give you some packages that we've predefined, so you can't install any additional packages. So that's defined as an input. We give it the resources that the agent itself configured. And then we run that sandbox. And so this is basically isolating the training loop, right? So this will do a little sandbox run, test out the idea that the agent had and how it might improve the LLM performance, and then come back with some metrics. Okay. At the end of this, we're going to append the results into a history list. So this just keeps track of the performance over time. And the first element of self-healing here is that we can actually catch out of memory errors, right? Both at the CPU and GPU level. And I haven't actually set up this code base to kind of intentionally raise out of memory errors, but I have seen them happen in my experimentation so far. And what this will do is it'll catch that error. And because we've isolated our training loop inside a separate container, this container that's running the agent is going to stick around, right? It's just going to catch the error, and it's going to have a second attempt at provisioning resources. And so we're going to catch the error here. We're going to feed it back into the provision resources LLM call, and it's going to adjust its resource requests based on everything it's seen so far, the code, the dataset, profile, etc., as well as the previous resources. And then on top of that, the error that it got. And then it's going to continue the loop, and then going to loop back and try the training job as well. So this self-healing number one is actually something that a lot of other orchestrators don't provide as infrastructure as context. So we're getting infrastructure-related metadata around the out-of-memory error that occurred. There's more that we could potentially give it here, but right now that's where we're focusing on sort of like the thing that happens most often, which is OOMs. And we're having the agent retry the code that it already has just on new set of resources. And so that'll loop back, it'll provision another container, and then run the experiment there. The other type of error here is just any type of logical error. So this, catch-all exception is going to catch errors that happen logically in the training script, right? So if the agent rewrote this training script and introduced a bug in it that caused a runtime error during training, what's going to happen is it's going to catch that exception. We're going to stringify that exception and then feed it back into the training code, right? If an exception didn't happen, error is just going to be an empty string, and then the agent's going to just run the next experiment. So it's going to take in the previous code, look at its performance, and then write the training code after that for the next iteration. In the end, we have some utilities here. Flyte report is the built-in native reporting system. It allows us to visualize what's happening as the agent is going. And in the end, we just have a data class of auto research outputs, including the history and all of that stuff. And so let's take a look at, hopefully this isn't a dumpster fire. Okay, the training loop is going on. If you're running this yourself too, you'll see that, this may take some time. But this is pretty much it. I can show you, an example of a previous run I did. In experiment 1, you can take a look here. The code is not formatted the best here, so let me look here. Yeah, so here's a report of the code it wrote. These are the constants. Let's see, I think, so the title of the experiment here is establishing a baseline with a larger model, LR schedule, flash attention. We would have to read through the code to see if it actually uses flash attention here. You can see it failed. You can look at the logs. You see that there is a logical bug. So we'll need to do some additional work here. I would probably just run this on Claude Code instead of just like a single pass through, one-shot pass through writing the script, right? So probably have another loop when the training code is being written that just makes sure that the code just runs and just double check for bugs. So this is, I believe GradScaler is in the AMP subpackage. But that doesn't matter because the agent just keeps going. It rewrote the training code. Again, as you can see, we gave it the previous code as well as the error that happened. Provisions additional resources again, runs experiment 2. Let's see what the log here is in the sandbox. Value error invalid literal for int. Okay, so looks like there is a bug in the data process, the loading of the tokens, right? So I think this should be a string, but it wrote an array of ints. I think it expected these things to be tokenized already. And then the third attempt, you can see that the training completed. I have a better example here that I ran before. Let me just go ahead and find it, of what this actually looks like. One second. Search. Okay. All right, so this is an example where I ran 10 experiment runs. The report in the end, you can see kind of a plot similar to the one I showed you, the original repo. You can see the best performing setting is happening over here. So over 100 similar types of runs, you'll be able to start seeing the performance over time. The one additional thing we would be able to do here with Flyte is to parallelize this, right? So in this agent, a limitation is that we're doing a single training run at a time. But you can trivially extend this such that you can have a LLM output 10 different training scripts and then run those in parallel in this inner loop, handle each one separately in terms of the errors that occur, kind of constantly update them, and basically fan out and parallelize the search strategy. So that isn't implemented here. That's something that you can definitely do with Flyte. Would be something I'll be extending this workshop code to do. So if you're interested, tune in to the workshop repo and look out for the changes there. But yeah, I think that's pretty much it. Hopefully, this gives you a sense of again, I'm using plain Python here, right? So when you hear the word agent, there's a lot of baggage that goes with it. But the way I'm kind of thinking about agents these days is, it's basically code we write that has LLMs or generative AI model as a component in it that does flexible things. So if you just look at this code and ignore the fact that there are LLMs here, it's basically just Python, right? There's a function that writes training code. And before, with deterministic programs, I wouldn't be able to implement this function in a reasonable amount of time, if ever. But now we have the tools that we can generate valid training code, run it, do loops, try catch on our errors, adjust to those errors. And so that's really kind of the point I want to hammer home here, is kind of like disenchanting all the hype words. And it's fairly easy to get going with this, right? So it's fairly easy to get a proof of concept out. At Union, I'm working with the team to build a lot of internal agents. And this is the story we keep finding, is it's fairly straightforward to get something going and prototype. With Flyte, it's easy to productionize, but then there's this constant iteration of improving the agent functionality based on the evolving requirements. So yeah, agents are just, it's more complicated than this, but they are really loops that have LLM calls in them. The self-healing aspect sounds fancy, but when you hear this out in the wild, this is something we talk about a lot too. But when you hear about this, it's really like, how do you adapt to the errors that are inherent in these kinds of systems? Because LLMs will write invalid code, they will have bugs. And it's just kind of the trade-off we have to make, that now you have these statistical token generators. If you instruct them well and you give them enough context, they will mostly behave in the way you intend them to. And so the self-healing really is just the term we attach to the fact that these things fail. And it would be nice if you have an agent in production, that it can kind of like help itself, update the code that it's writing, or in this case, reprovision container resources that's happening inside the agent's inner loop so that it can recover from infrastructure level failures. So I guess I'll end now. We'll have a little time if anyone has questions. I'll kind of stick around for a little bit, but yeah, in this case, we're giving it infrastructure as context. Right now, it's kind of thin. We want to really develop the story, but the infrastructure context here is that, hey, there was an out of memory error. So do something else rather than rewriting the code, because if the training code is very memory hungry, then updating the logic, like a logical bug, is not going to fix that. So you need to give it more context to be able to know, oh, actually it's a memory issue, so it's not a fix in my code, it's a fix in my resources. And I think the concept of self-healing goes up and down the stack, right? Goes all the way down to the infrastructure, all the way up to logical bugs and tool call errors. So yeah, I think that's all I wanted to share, and hopefully you learned a little something. This code is open source, so you can take a look at it. It's an adaptation of the Karpati auto research repo. There are some significant kind of changes at the edges where we kind of have to massage the data a little bit to work with Flyte. But yeah, it's effectively the same. And yeah, we'll be working on sprucing this up so that it can actually parallelize the experiments. Cool. Thanks, everyone. Yeah, I'll stick around. I may try to spend the rest of the time trying to parallelize this, so you can watch me flail around. Interesting design choice here. Yeah, I don't see any questions yet. But yeah, this is, do we do a single call to output n scripts, or n calls to output single script? And if we do n calls to output a single script, the likelihood that any given script will be the same is pretty low. But at the same time, if the model can handle it, which I think Claude Sonnet 4.6 can, we should be able to output, let's say, 10 scripts at a time. The nice thing there with the autoregressive nature of this is that it'll output script 1, and then as it outputs script 2, it has script 1 in its context. And so if you instruct the system prompt to say, generate n diverse scripts, hopefully that would change things. So let's see if that might work. I'm going to actually switch gears over to my local cursor here. And let's vibe this up. Update this function so that it outputs and scripts. Training prompt should be updated too, so the generates n diverse training scripts to test and make any downstream changes. Oh no, just have it do that much. So yeah, for a lot of work that I do these days, it's this is what it's like, and I'll be kind of multitasking between different either Claude Code or cursor tabs, depending on how I'm feeling. So yeah, pretty much that's the main change here is we want to output n scripts, and then inside we probably want to encapsulate all of this logic. No. So I guess that's another design choice here. Okay, train n scripts. What is it doing? Oh yeah, it's refactoring everything, right? Training code, okay. Oh. Nice. So, okay, now variants. So write training code now outputs variants. So the list of script titles and scripts. And then for each variant, it's going to run this. But we want to do it in parallel. Yeah, so we have to be careful here about how the exceptions are handled and how updates to each variant happens. So the way this is working right now, it'll be sequential still, because it does a for loop and then it awaits each subjob. So let's say so we need to keep a running list of all the exceptions that are happening in the parallel runs, either out of memory or logical. Collect those up. And then at the bottom, wait, where does it rerun? Oops. Okay, I can see some issues here already. See, coding agents will not, I mean, it did the thing, right? I'm pretty sure, I mean, there may be some bugs here, but this does make sense, but it's not quite what I want. So let's see, this section should run the run training subjob in parallel. Use a sync.io.gather to do this. you need to keep tabs on all the exceptions that are happening for a run. And re-add the, right? Yeah, where did that go? Yeah, this part. Bottom of the for loop. Update training code. Also take into account multiple errors that happened per variant. Oh, okay. Not sure if this will be enough information. Okay, so hopefully what I'm trying to do here makes sense. So we're trying to scale out the experimentation search space, meaning that we search more scripts like in the train.py design space at any given moment. Okay. So I think this was kind of what I had in mind more, was a helper function that handles the inner loop of the training jobs. And then it's keeping track of all the variant errors. And so this is mainly because I want to be cheap here. I don't want to do a separate LLM call every single time I generate a script. I want to cram as much context in every given call. And then it would generate, every time it's generating n hypotheses of what training a script would do better on the validation set. Okay, and then it writes this again. Did it I think it might have rewrote. Yeah, so it rewrote the training code such that it takes in previous variants and all the variant errors. Did it update the prompt as well? Yeah, it looks like it changed the prompt. And then, yeah, so scripts. Wait. Variants. Okay, so the variants are being added as user messages. That's interesting. Cool. Just have to make sure that the indexing is correct so that the script error matches the script itself. So another bug to look out for. Okay, well, I mean, the spirit of vibe coding, I'm just going to accept all and run this. Where am I? Okay. Well, we have 10 minutes. If anyone has questions, hopefully it'll show up on my stream chat here. But if not, we'll just see how well this works. Oh yeah, I guess another call out here is Flyte has caching. It's pretty nice to be able to cache the data. Which step was it? Oh, yeah, bundle, build auto research bundle, right? So we've cached this step, so we're not going to have to re-download the data set every single time. So I think it's probably at the script writing phase right now. It's going to take a little bit. Nice, okay. So it wrote a bunch of training code. This looks like a bug. So item 0 is just a string, and then item 1 looks like the whole script. Okay. Cool. Well, you get the idea. We'll continue iterating on this, and I'll post this up, the complete parallelized version of this up on LinkedIn socials when it's done. Yeah, I'll end the stream there. Thanks, everyone. Thanks for tuning in. See you later.